In this clip, we would like to test the general case algorithm on integer subtraction, decimal fractions, and mixed numbers. From 12,250, I am going to subtract 5,375. I'm going to use the textbook algorithm first. 9's complement procedure, subtraction by addition next, and we can compare the two procedures. Five is greater than 0, so I have to borrow 1 from this 5, that becomes a 4, this becomes a 10. 7 is greater than 4, so I have to borrow 1 from this, that becomes a 1, this becomes 14. 3 is greater than 1, so I have to borrow 1 from this 2, that becomes a 1, and this becomes an 11. 5 is greater than 1, I have to borrow 1 from this, it becomes a 0, and this becomes an 11. So the minuend has been modified now to read 0, 11, 11, 14, 10. How many number transformations did I do? 1, 2, 3, 4, 5, 6, 7, 8. 8 number transformations. Now that I've modified the minuend, I can do the subtractions. 5 from 10 is 5. 7 from 14 is 7. 3 from 11 is 8. 5 from 11 is 6. 0 from 0 is 0. So my difference is 6,875. How many operations did I do? 8 number transformations, and then 4 hard subtractions. 12 operations to get my difference using the textbook algorithm. Now we'll do the same problem, subtract by the 9's complement procedure, subtraction by addition. I will take the minuend and rewrite it without modification. We are not at all concerned with the minuend in subtraction by addition. This subtrahend has 4 digits in it, and the minuend has 5, so I must add a leading 0. You must add as many leading zeros as you need to make the subtrahend digits equal to the minuend digits. What number added to 0 equals 9? 9. What number added to 5 equals 9? 4. What number added to 3 equals 9? 6. What number added to 7 equals 9? 2. What number added to 5 equals 9? 4. Now I'm going to proceed to add. 4 and 0 is 4. 2 and 5 is 7. 6 and 2 is 8. 4 and 2 is 6. 9 and 1 is 10. So my first operation, I get 106,874. In subtraction by subtraction, I am subtracting 5,375 from this number, so I get a smaller number. In subtraction by addition, I am adding 94,624 to the minuend. I am going to get a carry. It will always be a 1. 1 decimal place greater than the minuend. Notice that these 4 digits are almost equal to the difference. It's only off by 1. In the nines complement procedure, it is mathematically correct to take the leftmost digit, which would always be a 1, and add it to the rightmost digit, 4 in this case, and you get the correct difference, 6875. And we did it by addition. And the modification of the subtrahend does not depend on these numbers, minuend numbers at all. You're always going to take the nines complement and then just add it. The textbook algorithm for subtraction by subtraction is the most difficult way possible to do subtraction. Subtraction by addition is the easiest for one fundamental reason. Addition is much easier to do than subtraction. As a matter of fact, addition is the easiest operation to do in arithmetic. If we take our original problem, 12,250, and add a decimal point there, and our subtrahend we add a decimal point there, and we're going to get a decimal point in our difference. But all the numbers will be the same. All the modification of the minuend and then the hard subtractions, all the numbers stay the same. We get 6.875 difference. 5 from 12 in this case. Same with the subtraction by addition. Those are the numbers that were the nines complement of the subtrahend. The last step is to take this 1 after you add these, take that 1 and add it to that 4 and you get 6.875. Same difference. So the procedure essentially ignores if it's an integer number or a decimal fraction. In this clip, we will convert this decimal fraction into a mixed number. 12.250 is 12 1/4. I want to subtract 5.375, and that is 5 3/8. Our difference was 6.875, and that translates into 6 7/8. Now this is eighths and this is quarters, so I'm going to immediately multiply by 1 and substitute for 1, 2 over 2. 2 over 2 is another way of writing 1. 2 divided by 2. 2 times that is 2. 2 times 4 is 8. So I got 12 2/4. 2 divided by 8 is another way of writing 1 divided by 4. So I'm going to proceed 12 2/8 minus 5 3/8 should equal 6 7/8. But I'm going to do it by the nines complement procedure. I must find the nines complement of this subtrahend, 5 3/8. So I'm going to add a 3 to that 5. I'm going to get an 8. I want to add 5 to this 3, and that'll give me an 8. 3 5/8 added to 5 3/8 is equal to 8 8/8. And that's another way of writing 9. So 3 5/8 is the nines complement of 5 3/8. Now I'm going to proceed to add 12 plus 3 is 15. 2 eighths and 5 eighths is 7 eighths. The last step in the nines complement procedure is take this leftmost 1 and add it to the rightmost 5, in this case, and you get a 6. So you get 6 7/8. In this clip, we will summarize subtraction by addition using the special case algorithm for students in the first grade, and general case algorithm is valid for all numbers. We have shown that subtraction by addition using the 9's complement procedure, we can do integer subtraction, we can do decimal fractions, and we can do mixed numbers. So we can do it all. And we will show also an alternative method of subtracting, which avoids borrowing. And we could do that by modifying the minuend ever so slightly. We'll show that also. From 4,567, we want to subtract 789. I am going to take the minuend and decompose it into two numbers, 4,000 and 567. So we express it as two numbers. Then what I'm going to do is subtract 1 from 4,000 and add 1 to 567. When I do that, I get 3,999 and 568. When these two are added together, you will get 4,567. Now I'm going to proceed to subtract 789 from 3,999. 9 from 9 is 0, 8 from 9 is 1, 7 from 9 is 2. And then I'll bring down that 3. Notice something, these three numbers are the 9's complement of 789. So 568 added to this, 8, 6 and 1 is 7, 5 and 2 is 7, bring down the 3 again. So I get 3,778 is our difference. How many operations did I do? I did 3 easy subtractions, 1, 2, 3, and 3 easy additions. So I did 6 operations to get that. If you modify the minuend such that you maximize the number of 9's, then you can do subtraction by easy subtraction and then add the partial minuend at the end to get your difference. It's an alternative, and it sort of leads into the 9's complement procedure that's valid for all numbers. Anyway, I have 4, 5, 6, 7, and the 9's complement of 7, 8, 9 is this 210, 210. Now I have to add a leading 0 because there's only 3 digits, and there's only 3 digits in the subtrahend, and there's 4 digits in the minuend. So I add a leading 0, and when I take the 9's complement of that 0, I get a 9. So I have 9, this is the 9's complement of 0789. I proceed to add it. I get a 7, 7, 7, 9 and 4 is 13. So these 4 digits are almost correct. They're only wrong by 1. Now the last step in the 9's complement procedure is take this leftmost 1, it will always be a 1 in the 9's complement procedure, and add it to the rightmost digit, 7 in this case, and we get the correct difference, 3778. This method here could be a lead-in to introducing the 9's complement procedure valid for all numbers. Here is the special case algorithm that we showed in clip 1. 14 subtract 6. 1 and 4 is 5. I wrote it as a subscript. 9's complement of 6 is 3. Add these two, 5 and 3, 8. You get the difference. The student in the first grade could do that once they have acquired the skill necessary to add two basic numbers that sum to 9. When they can do that, they can be taught subtraction by addition. Special case algorithm is valid provided the minuend is in the range 10 to 19, and the subtrahend is one of the basic digits. In other words, 2 to 9. There's an alternative here that we just shown. If you modify the minuend, express it as two numbers, and modify it in such a way to maximize the 9s shown in one number, then you can do easy subtraction and then followed by addition. To summarize, we have an algorithm that we can teach students in the first grade to do subtraction. They won't understand why the 9's complement procedure is accurate, but by repeated use of the algorithm, they will learn the facts in the subtraction table automatically. They don't have to memorize them. Memorizing abstract facts that cannot be visualized is the most difficult memorization possible. So it's much better that students verify it. Later on, I don't know, second grade, third grade, you begin to introduce the not only the textbook algorithm, but the 9's complement procedure for doing subtraction by addition. Why teach both? Because, for one fundamental reason, addition is much easier to do than subtraction,